And don't forget, all of that I already have there in my YouTube channel, right? All the recordings of last year. Last year for this course, I have them in YouTube. It just there are some minor differences from what I recorded last year and this year, but there are some differences nonetheless. What I want to do for this chapter is the following. We are on chapter 10 right now. Okay, for chapter 10. And we will cover the following sections. Already sharing the screen. You go. The ideal spring. We already did that. Okay, so let's shrink a little bit here. Uh, 10.1, the ideal spring. 10.2, we did that too, simple harmonic motion and reference circle. Well, I would say, instead of saying the reference circle, I would say NUCM, right? There's a relation, there's a very close relationship between simple harmonic motion and uniform circular motion. The projection of either the X or Y axis in a uniform circular motion, the projection along the X or Y axis, right, results in the exact type of simple harmonic motion. So we can say that it's, it's not out of this world to state that simple harmonic motion is one-dimensional motion, the circular, one-dimensional is the one-dimensional component of uniform circular motion. Okay, can you remember that? Okay, it's not far off. It's not far off to state that SHM is the 1D component, either X or Y of UCM, of uniform circular motion. It's not far off to state that with the proper adjustment of the parameters, right? With the proper adjustment of the parameters. That 10.2. We're going to do now 10.3, which is energy and simple harmonic motion. Simple harmonic motion. And we are going to finish this chapter is 10.4, the pendulum, the simple pendulum. Okay. Simple pendulum. The simple pendulum. And there is also the physical pendulum. Let's see if we have time to cover that. So the simple and physical pendulum. Let's see if we can cover the physical pendulum as well, which is not that much different. Everything else I'm not going to cover. Damped harmonic motion, driven harmonic motion, resonance, elastic deformation, stress and strain. Okay, let's stay within this part here. Okay, so recall the types of. Now I can blow it up here. I don't need to look. Recall the types of conservative force. Right? The weight, and when I mean the weight nearby their surface, weight nearby Earth's surface, which is going to be mg. The weight at any arbitrary distance from the center of the Earth, which is that formula a little bit more complicated, right? Big GM, okay, divided by R squared. That's universal gravitational law. And the other type of conservative force that we saw was Hooke's law. Hooke's law. Hooke's force law, which, by the way, ends up being the simple harmonic motion. Okay, those are the three important types of forces that we have. No, and it's very important that you memorize that. There are more, but those are the three that you must know by heart. Okay, because simple harmonic motion is dependent, right, on Hooke's law. Hooke's law, comma, then there must be a potential energy for this type of motion, right? Okay, and just to remind you, right, for our first type of law here, the potential energy here is going to be what? That's easy to remember, right? Insert. I'm going to put here the potential energy U equal to mgy, right? Oh, is U, not V. Why did I put V? The other one is a little bit more complicated. U, big G, big M over R. Okay, and Hooke's law. Do you remember Hooke's law? The potential energy for Hooke's law. U here is going to be half AX squared. Okay. And the potential energy for the simple harmonic motion is going to be this expression that you see right here. Okay. And Hooke's force law, I'm going to F equal to minus KX. Okay. So assuming that there are no friction, right, acting in the mass attached to the spring, and what does it exactly? Let's be even more genetic. Instead of saying that there are no friction, assuming that the only forces acting in the mass attached to the spring are conservative forces, then it follows that mechanical energy must be conserved, right? Mechanical energy must be conserved, or mechanical energy in this case is going to be kinetic energy plus potential energy. Kinetic energy is mv squared plus potential energy kx squared. And now going back to our equations for velocity and position of a mass under simple harmonic motion, right? You're going to see that mechanical energy is going to be conserved automatically. Okay. And how do we do that? Let's go back to our equations for the position and velocity. Going back right in here. Here you go. I'm gonna copy those two. That's all we need, right? To demonstrate, to prove conservation of mechanical energy. X, let's see here, go mv square, mv square is right in here. X square is right in here. Okay. And we can go ahead, expand that to get x squared k over m sine square. Let's see again. Right? Kx naught square cosine square like that. And what's going to happen? M cancels out with M. See that we end up with kx naught square, which, by the way, we have kx naught square as well as half. And then we have that nice relationship between sines and cosines, right? So that was going to be the next step here. The next step, the mass is going to cancel out with this mass. Okay, the k here is going to be multiplying x naught square in front of it. We are going to place kx naught, half kx naught in evidence. More students coming. Wait. Okay, good, I got it. This term here was already factored, and look what we get. Mechanical energy is going to be equal to half kx naught squared, which is a constant, right? Which is a constant. So if you have a problem, so here you go. Suppose that so suppose that we have an example, right? Example. The initial position and velocities of a mass attached, an object of mass m, right? An object of mass m attached to a spring of constant k, right? Oh, let's put it this way: an object. Let's rephrase that. An object is attached. An object of mass m is attached to a spring of constant k. If it's initial position and velocities are known, x naught and v naught, find the the particles velocity at the position of equilibrium. Solution. The position of equilibrium. Don't forget position of equilibrium, right? Would be xf is equal to 0, right? That's what position of equilibrium is all about. So all we have to do, one way to solve this problem, okay? One way to solve this problem is by using conservation of energy. Or, na verdade, já está explaining if its initial position velocities are known, assume, right? Assume that the only force acting on the mass is the elastic force. Assume that, not the only force, assume that the net force acting on the mass is the elastic force. By using conservation of energy, okay? That's one way. So conservation of energy is gonna be like that. Final mechanical energy is equal to initial mechanical energy. Okay. Final kinetic energy minus final potential energy is equal to initial kinetic energy plus initial potential energy. We know V naught and X naught. Okay, final kinetic energy is half m Vf square. Final potential energy is going to be 0 because Xf is equal to 0. Initial potential energy is this one right in here. And initial potential energy is half kx naught square, like that. We know X naught, you know V naught, and we're trying to get the Vf, right? Two is going to half is going to disappear. If we pass m to the other side, this m here is going to disappear, and we're going to end up having k over m, and the final velocity will be given by this expression that we see right here. Okay. And we can repeat, we can repeat example 1. Repeat the above. Example 2. Repeat the above. For the for the position, let's see, assume that for find the particles for the, repeat the above for the position of the particle at maximum amplitude. Okay, don't forget that at maximum amplitude, dF is going to be equal to 0. Okay. Like that. So you try to do that on your own. Okay, I'm not gonna, but practice at home. Practice at home. In this in both cases, okay, notice that the particle is not necessarily at maximum amplitude. The particle is located at the genetic position in which it has a velocity, right? So x naught here is not going to be necessarily the amplitude of the particle. The amplitude of the particle is going to be something else. Okay? So that's example 2. And next thing that we're going to do, we did that, right? Mechanical energy. Conservation of energy, blah, blah. And now what we're going to do? Simple pendulum. Simple pendulum. Let's go take a look at the drawing for the simple pendulum. It's going to be like that. Okay, what's the simple pendulum? Is a string attached, a big mass M attached to a string. Okay, the mass of the string is much smaller than the mass of the object. Can be neglected, and by neglect I mean the mass of the string is at least 10 times less than the mass of the ball. If you neglect the mass of the string, this thing here behaves as though it has just all the mass concentrated at this point here in which it's going to oscillate, okay? And how do we solve this problem? Okay, we solve this problem by doing exactly what we have been doing since we started working with Newton's law of motion. We're going to identify the forces that are applied to the object. In this case, it's going to be the weight of the mass and the tension. Okay. Here you go. Here the X and Y coordinate axis. Okay, but we are better off, but instead of putting the origin right here, we are better off putting the origin right in here to facilitate the solution of this problem. Okay. And here you go, we identify the forces. Here you go, what you have to know. Now that we changed the coordinates, the origin of the coordinates, we are going to use not the Cartesian axis, but you're going to use the polar coordinate system. In this case, for the polar coordinate system, we are going to have two different coordinates. It's going to be the r, the radial component, right? And the theta. Instead of xy, it's going to be r theta. What you see right in here is the unit vector along the radial direction. Unit vector along the radial direction. And what you see right in here is the unit vector along the theta direction. And it's supposed to be subscripted here. And this one supposed to be subscripted. And now we don't need to put that. We don't need subscript here. I'm just being lazy and not writing the hat there at the top. Okay, that's what I'm doing here. Leave this way. Right? So here you go. It just happened in this type of coordinate system, in the polar coordinate system, the distance from the origin is going to always be constant. It's going to be the length of your string. Okay, it's going to be the length of the string. And we can identify now. We identify the forces, right? And this problem can be solved more easily if we use the torque, the equation for the torque. Okay, Think about that. This is a point mass that's subject to a torque. And the torque that it's subject to is the torque of this force right in here. Okay? Do you see that? That the point of application, the vector position of the point of application of the force that goes from here to here, right? And the force that applying the torque is this one. The tension is not applying the torque. The tension does not apply the torque because it's it's lined up in such a way that doesn't produce any torque whatsoever, right? The tension is collinear with the vector position. So the only force that applying the torque is this mg. And we can write that down, that, the net torque applied to the mass is going to be given by the radial component of the weight times the distance from the point of rotation, which is L. But because this force here is contrary to that angle theta, we call it a restoring force, we must have a negative value right in here. Okay? In the next step, okay, to solve this equation here is rather difficult because we have this sine of theta. Let's write it down. To solve the above equation, even using calculus, right? It's difficult. It's difficult to solve the above. It is difficult to solve the above equation, even using calculus. For this reason, we use an approximation that is very useful and effective for small angles. And this approximation is going to be what? Sine of theta approximately equal to theta for small angles. When we have small angles, the sine of theta is going to be very close to theta. And I believe I did, I demonstrated that for you, right? Did I demonstrate that for you? Let me see if I demonstrate that for you in Excel. I believe I did. If I didn't, I'll do that again. I'm going to prove to you that sine of theta is approximately theta. Let's see if I have it here. It's not difficult to do that in Excel. Yeah, it doesn't look like I have it, but I'll do it. Okay, so here we go. I'm going to theta, right? Don't forget, we have theta in degrees, and we have theta in radians as well. And here I'm going to use sine of theta. Symbol. And here I'm going to use it. App script, superscript. Symbol. And I put symbol here as well. Right? So let's see. I'm going to start with 0, 1, 2, 3, and so on, right? Degrees, all the way up to 90 degrees. And you're going to see that the approximation that I mentioned applies, but it applies only if you use the angle theta in radians, okay? What radians? Gotta put a plural here. And then I'm gonna take the sine of this angle in radians, right? So see that? What happened here? Okay, I put the wrong one. For theta equal to 0 degrees, the sine is the same, right? 0 degrees, 0 radian, sine of theta is going to be 0. So that's a perfect equality. And what happens when you go to different angles? Let's take a look. See here, sine of 1 degree, which by the way is this much radians, is going to be very close to the radians. See that 0.017452 is only this 1, 2, 3, 4, 1, 2, 3, 4, the 6th decimal place that changes. We keep on investigating the rest. You know, 1, 2, 3, up to 1, 2, 3, 4, up to the 4th decimal place whenever you are 2 degrees. Those two are very close to each other as well, right? And I can go ahead and I can calculate the percentage difference. Okay, here the percentage difference is 0. I'm not even going to do the calculation, okay? But to calculate this one, absolute of 1 minus the other divided by the actual value, and then I'll multiply by 100%. Do you see here? It's 0.005%. The difference is so small that you have a very small percentage difference. And then we can keep on doing that up to 90 degrees, okay? If you want. Take a look. Take a look what we get. As the angle starts increasing, the percentage difference between the approximation and sine of theta starts increasing too. But it's still very small. It's 0.3% only. Remember that I told you anything less than 5% is negligible, right? Sometimes we can go even up to 10%. Anything less than 10% is negligible. Here we're at 12 degrees here. See, we're at 12 degrees here, and we have only 0.7% difference between sine of theta and theta. So this approximation, sine of theta approximately equal to theta, is a very good approximation. If you keep investigating this spreadsheet, you can see that all the way up to 30 degrees, you have only 5% difference. You know, instructors usually tell us that this approximation sine of theta approximately equal to theta is good only for 10 degrees or less, okay? That's what people usually tell us. Well, I beg to disagree, okay? The approximation is good up to a point of what you consider negligible, right? If you consider, let's say, 0.5% difference, above 0.5% difference, not negligible, then you can say that that approximation works up to 10 degrees. But if you are a little bit more lenient and say, look, up to 5%, you know, 5% is going to be negligible. Up to 10% is going to be negligible. So then we can come back and say, look, we can use that approximation all the way up to 31 degrees, okay? Or if I come to you and say, look, since you are undergraduate students, I'm going to, right? I come to you and say, since you are undergraduate students, I am a little bit more lenient with you, and I will consider negligible anything that less than 10%, right? Okay. And if you go all the way up to 10% difference, 10% difference for that approximation is going to be around 43 degrees. Okay. And let's see, let's keep on going. I want to go all the way up to 90 degrees, right? And let's see what's the percentage difference between, now when it gets all the way up to 90 degrees, we get a 57% difference. Okay, this is not negligible. Half, more than half, right? This is not negligible. So this the approximation of sine of theta, approximately theta, doesn't apply in this realm. Doesn't apply at it doesn't apply at 90 degrees, okay? And you can see, right, 40% difference, right? I would say it applies all the way up to 45 degrees, okay? At 45 degrees, you have 11% difference. If you want to be a little bit picky, you just say 43 degrees, but it's 45 degrees is easier to remember, okay? So that's what this approximation, that's how this approximation works, okay? The above, I'm going to write it down here for this. The above approximation is good within 10% for angles. I'm going to be even more 11%, right? Within 11% for angles less than 45 degrees. It's very, approximations in physics and math are very important, okay? That's why I hit in this button over and over again. Let's see here. Approximations help you solve problems more easily and within a very good high degree of accuracy if you are within, certain ranges of values. So why am I doing that? Because when I substitute the sign of theta right here, it becomes easier for us to figure out what is going to be the angular velocity of my simple pendulum, okay? So now that we found out the sine of theta is approximately equal to theta for angles of theta is small, for the small angles of theta, I'm even going to put an approximation here. So you understand it's not an equality, it is an approximation, but again, it's a very good approximation. Keep that in mind, it's not any type of approximation. And I'm going to do even one more thing. I'm going to put this theta angle right in here after L. Okay. And I'm going to use that other relation that you know for the net torque, which is equal to I, right? Remember, net force is equal to mass times acceleration, right? Net torque is going to be I times angular acceleration, right? That's what we have. So we get, and by the way, the approximation also is going to come right in here. That would be the right way of displaying this equation. Okay, with the approximate sign here, you cannot put an equality here because this guy here is not equal to this one. This guy here is equal to this one here. Okay, here we have the approximation. And then because the simple pendulum is a point mass, okay, the moment of inertia of the simple pendulum is going to be ml squared. Okay, I put the equal here because I'm talking about this equation here, okay? That's why I put an equality here. But if I'm going to rewrite this equation just with the mgl theta, then I have to go back to the approximation sign. And when we do that, the L cancel with the L, the mass cancel with the mass. Okay. And then you know what? I did that too early, but that's the relationship that we get, right? So let me go one more step here. The alpha is going to be approximately g theta over L. But going back to what I had before, okay? I want to show you a nice correlation between what we have what we have here and something that we did before, something similar that we did before. Something similar that we did before was for the spring, right? For the simple harmonic motion. Remember that? Net force is equal to minus kx. And it's not an approximation. This one is an equality. This one is an equality. Okay? So I'm going to put that the above is for the simple pendulum. The above is for the simple pendulum. The above equation, right? The first equation. For the simple pendulum, comma. The second equation is for simple harmonic motion. A mass attached to a spring. Mass attached to a spring. And now we can start looking at what corresponds to what on those two equations, okay? So what we have here we have one of the coordinates, which is x, and here we have the polar coordinate theta. This k that you see right in here corresponds to this constant that you see right in here, mgl. Notice that the negative sign here, we have a negative sign there upstairs as well as a negative sign downstairs. Here is the linear inertia that I mentioned to you, right? And here is the angular inertia. Here is the acceleration, and here is what? Here's the angular acceleration. In view of those relations, I can go ahead and call this MGL here a K prime. Okay? I can call that a K prime. Comparing, x, let's see, the coordinate x in the above equations, the SHM x, the SHM coordinate x correspond to the angular coordinate theta, and the linear acceleration A corresponds to the angular acceleration alpha. I'm going to be a little bit lazy here. I'm going to just spell out alpha. And then this one, we go theta. Okay. Consequently, the K in the second equation corresponds to an angular K that I call K prime. K prime given by, we usually do those analogies in physics to understand the problem better, okay? MGL, okay? I'll go the next step here. I'm going to write this equation because we're going to use it again. Okay, but now I'm going to write like that. K over M here on the left side. MGL over I here. No M, no I. Both I and M are constant. Okay? And then we go back. Then we go back to the equation for angular velocity of a mass attached. Angular velocity, no, angular frequency, sorry. It's not angular velocity, angular frequency of a mass attached to a spring. Do you remember that? The angular frequency, which we called omega, is equal to what? Square root of K divided by M. K divided by M. Okay, but recall that my corresponding K prime for the angular quantities is going to be MGL, right? And the angular mass is going to be I, right? So this K over M should be substituted by MGL over I, right here. That's the angular frequency. We can do better. We can do better. We can, now I'm going to replace the I by the moment of inertia of a point mass, which is ml squared, right in here. And I'm going to come to a result that's simpler. L squared cancel with L. And here what we get for my simple pendulum. Here what we get for the angular frequency of my simple pendulum. Angular frequency of the simple pendulum, omega, is square root of G over L. Which, by the way, is 2 pi times the frequency, okay? 2 pi times the frequency, which, by the way, see, that's why we call angular frequency, right? Because it's directly proportional to the frequency, and it's directly proportional to the frequency, and it is also multiplied by 2 pi, right? With the frequency multiplied by 2 pi. So here you go. This guy here would be the angular term, right? Angular frequency. Can you remember that? Angular 2 pi frequency F. And let's not forget that the frequency is the inverse of the period. Okay? The inverse of the period. That's how we can go another step to find the period of my pendulum. Okay, in terms of the length of the pendulum and the acceleration of gravity. Right? I go ahead and pass this term to the other side. L over G. And here, that's what we end up having for the simple pendulum, the period for the simple pendulum. And now I can display, here you go, the equations of motion for uniform circular motion. Here goes uniform circular motion, simple harmonic motion, and simple pendulum. Okay. We get something similar for the linear velocity of UCM, linear velocity for the SHM, simple harmonic motion, and the angular velocity, right? The angular velocity. Notice that I put omega prime here because omega I'm using as the name for the angular frequency, not the angular velocity. Angular velocity equal to this term right in here. Wait a minute, there's something wrong here. Here's cosine. Okay, here is supposed to be sine, okay? Yeah, here's supposed to be sine. Remember? Cosine turns into sine turns into cosine, right? And then go. We here write, now we write the acceleration, right? UCM, and here's cosine. Here's cosine. Okay. Equations of motion for the following cases. One, the X component of the position of a mass undergoing uniform circular motion, right? The position of a mass attached to, and I'm going to even put the linear position, right? Position of a mass attached to a spring of constant K, right? Of the position, I'm going to put it position, velocity, and acceleration, right? The linear position, velocity, and acceleration of a mass attached to a spring of constant K. And finally, the angular position, velocity, and acceleration of a mass attached to a string, right? Simple pendulum, the simple pendulum. A string of length L. Those are the equation of motion for all those three cases. If I put that in a table, tables are very nice. You know, you folks have to practice understanding how practice reading tables, and then later on, you know, it's very difficult to build a table. Okay, it's not easy. You have to have a certain set of skills to build a table. Okay, so at this point in time, the first thing that you have to do, you have to understand, you have to read a table. And then later on in your life, you are going to learn how to build a table from scratch. Okay. Like I said, you know, coming up with a table is not something easy. You have to have a very good mastery on how to do those things. Here in this case here, you know, instead of putting the angular position of the pendulum, I wrote down the parameter S, which is the arc length in the above, okay? In the above, S is the arc length of the simple pendulum with respect to the point, with respect to its point of equilibrium. Okay? Point of equilibrium. And the nice thing about the original, and I'm going to go one more step here that I didn't do, okay? Instead of substituting this I right here by ml squared, I'm gonna leave it like that. Why am I doing that? There's a reason why am I doing that. If this equation applies to a point particle undergoing an oscillation, a simple, what we call a simple pendulum, if I preserve the I and not spell it out right in here, what you're going to end up having here is going to be the generic angular frequency, not for the simple pendulum, but for a physical pendulum. Whereas a physical pendulum is that object, that rigid object that's put to oscillate back and forth. Okay, so let's see if I have an illustration here of a physical pendulum. Unfortunately, I don't have it. I must have it somewhere in there. Okay, but let me see if I can draw that for you. Okay, a physical pendulum is going to be something like that. Let's see here. Okay, like that. a rigid body of mass m. Okay, rigid body of mass m. It's not a string. I don't this let's say the center of mass of this guy is somewhere around here. Position of the center of mass. I don't like this one. Let me do a better one. Let's see. Yeah, better like that. Okay, let's do like that. Here you go. Here's my rigid body. Point of oscillation is right in here. Okay. And let's say the center of mass is right in here. Center of mass. I'm going to this guy here. Let's say the distance from here to here is a distance. I'll call that distance L. Okay. I'm going to change the color so it doesn't disappear there, right? Bring it to the top. Yeah. The distance from the point of rotation to the center of mass of the rigid body is O. This L. I'll take the L. No, wrong place. There you go. I don't need this guy anymore. I don't need this guy anymore. Okay. And by the way, I would say that this not only has a mass m, but it has a moment of inertia I. Here's the angle theta. And here we're going to have my weight applying a torque to this rigid body. And now I can add one more equation to my table. And instead of simple pendulum, I'll write it down physical pendulum. Okay? The equations are going to be very similar. Let's see here. I'm not going to, you know what? Let's see. Let's see. Here you go, like that. And I'm going, instead of using S, I'm going to use theta here. Okay? Just to simplify things here. And this one is going to be omega. Oh, don't forget, it's an omega prime, right? For angular velocity. And that's going to be alpha. Let's see here. Let's see. Alpha. And we got to be careful here what goes there. It's going to be theta naught G over L. Yeah, theta naught G over L. Here should be G over L. Let's make sure, right? Omega prime, yeah, G over L. And we get the same thing for the physical pendulum, exactly with the exception of what goes here inside this square root, right? And this square root as well. 1, 2, and 3. And by the way, I will even see we have a G over L here as well, right? If we go back, let's see, where's my, yeah, the equation is right in here. Here's the relation. What is G over L is mg over Li, okay? You go. You go. You go. And here you go. Right? And here we go. So if you ever find a problem of a physical pendulum, you already know the result. You already know the equations of motion for the physical pendulum. Yeah, it's almost the same, with the exception of the term that shows up in the argument of the sine and cosine. Oops. Sine and cosine. Did I get everything? Yeah, I need to replace this one here. Okay. So 4 different types of problem that are related to each other. The physical situations are distinct, but mathematically speaking, they are almost the same. Okay? In the above cases, the physical, I'm going to take out the S. I don't need the S. In the above cases, the physical situations are distinct, but mathematically, they have almost the same solution, right? And that's what I want to cover for this chapter. We did sections 10.1, 0.2, 0.3, 0.4. And I want to have a break. Let's put our break at 10 o'clock a.m. Right? Let's not go into the break yet. Let's get attendance. Do you have any questions? Roster right here. Oh, that's the roster. And today is the 27th. Let's see here. I don't see Sky here.
I'm here.
Oh, you're there. Okay, thank you. Sorry for not seeing you. Is Gael there? I don't see Gael. Next is Ridwan. You're here, right, Ridwan? Just say you're there. Yep, thank you. Ashley, are you there, Ashley? I don't see Ashley there. Norberto Lopez.
Oh, I'm here.
Thank you, Norberto. Vanessa Mena.
Here.
Thank you. Catherine Pacheco. I don't see Catherine. Let's see, Camden is here, right? Just say you're there, Camden. I'll give attendance to him. Okay, he's always the first one to arrive. Marco Sanchez. Hello, Marco. Okay, good. Camden applied. Okay, Marco is there. Good. And we have a total of 6 students. Good. So any questions? Let me adjust my break time here. Oh, by the way, that's what we're doing. I'm gonna put the 10 here, right? I plan to start fluids today. Fluids, that's simple harmonic motion, fluids, thermodynamic. Let's see if we can do thermodynamics 1 and 2, right? Thermo 1 and 2. So it fits there. And here's the lab 6, uniform circular motion. Fluids. Looks like we're going to skip that because I want to get into waves and sound. Okay. 9:58, 10, 12, 13. Okay, so that's the plan. And okay. Let's see, 9:58. Okay, so you don't get undersold here. And 12, 10, 13. We're back at, oh, no, 59. Here you go. 10, 14. I see you in 15 minutes. Okay. I'm back here. Now, I want to warn you, right, about this L here. Okay. Let's say this L here and this L here. Okay. I'm going to, don't forget, this L here is the distance of the point mass to the point of rotation. Whereas this other L here is the distance of the center of mass of the rigid body to the point of rotation, okay? So that's why I illustrated in this way. It is as though all the mass of this rigid body would be concentrated here at this point, okay? But in order to make it, to make it explicit, right, that this L corresponds to the distance of the center of mass to the point of rotation, I'm going to call it L prime. So you know that there is a difference between those two, okay? We put it L prime here, L prime here. And I want to make it look better. I don't want two lines here. Let us get a little bit more of space, right? So the alpha and the omega end up in the same line. Okay, now it's better. Okay, and I'm gonna write that down here too, in the above equation. In the above equations, comma, L is the distance of the point particle, the point mass, right? The point mass to the axis of rotation, and L prime is the distance of the center of mass of the rigid body to the point of rotation. Okay? So that's the important difference between those two. And I will insert my page break here. And what we're going to do now, we're going to do chapter 11, fluids. Okay. Let's take a look here. What we have here for fluids. We have the concepts of mass density. I'm not going to cover everything, just like in the other chapters, okay? So what we're going to cover? We're going to cover mass density. We're going to cover pressure. We're going to cover pressure and depth in a static fluid. And then we are going to skip to the Archimedes principle. Okay. Everything else, we won't have time to cover. But if you want to know by yourself, you can read it on your own. It's not going to show up in the exam, but it's still important. Okay. Keep in mind, right? Not everything that everything that I teach here is important. And there are even other things that are also important that I don't have time to teach. Okay. But those are the chapters that we're going to cover: 11.1, 0.2, 0.3, and 6. I'm gonna write it down here, and that's what you have to worry about the exam. But it's not just because I'm skipping those chapters, those sections that are not important. Now they are important. Okay. And you should, if you want to know about them, you might want to take a look on your own. Okay, chapter 11. Let's see, section. Okay, we have it here as well. And let's see. Let's take a look at chapter 9. Right, what we cover for chapter 9. I want to keep everything in the same spot. Here's my chapter 3, exam 3 was 5 through 7, right? So let's take a look at chapter 8 and 9. So we have everything organized here. Chapters 8 and 9. Yeah, it doesn't look like I wrote anywhere. Let's see if I got it for chapter 8. Oh, yeah, 9. Here you go. Chapter 9. I will copy and paste when I find the chapter 8 here. Okay. Chapter 9. So that's gonna be 8. I don't like when he does what it's not supposed to do. 8.1. Let's try it again. Not good, not good. 2, 3, 4, 5, 6. 8.1. Yeah. You know what? It's sometimes it's really annoying when Word does that, and I still haven't figured out how to prevent that from happening. Okay, so here you go. So you go ahead, you just take a look at the book, right? And figure out what sections those correspond to, right? One must be 1, 2, 3, 4, 5, 6, and 7. Maybe that's what it is. And 8. Let's see. Rotational kinematic. 1, 2, 3, 4, 5, 6, and 7. Yeah, that's right. Follows accordingly. Okay. 8.1, 8.2, 8.3, 8.4, 8.5, 8, 1, 2, 3, 4, 5, 8.6. 1, 2, 3, 4. Okay, 1, 2, 3. Oh yeah, I put it in the wrong place. Okay, and if I'm accelerated rotational, here you go. Yeah, here you go. That should be 1, 2, 3, 4, 4, 5, 8.6, and 8.7. 1, 2, 3, 4, 5, 6, right? Did I miss anything here? 1, 2, 3, 4, 5, 6. Yeah, I covered everything. Simple harmonic motion, you already saw what it is. That's right here. Chapter 10. Sections, right? Chapter 11. Mass density, pressure and depth in a static fluid, and Archimedes principle. We're going to cover all those topics alone, only. So fluids. Okay, the first idea that you have to know, about fluids is the concept of density or mass density, okay? That's the first idea you have, the first concept that you have to know. If materials are made of the same substance, they are going to end up having the same density, even though they do not necessarily have the same mass, okay? And because of this characteristic among materials of same composition, we come up with the definition of density. Density, here you go, let's write it out. Density is an important concept because materials made from the same object, right? Materials of different masses and volumes made from the same substance have the same density, has the same mass density. The book says mass density, but in general, we just say density, okay? Or density. Accordingly, density is defined in the following way. Do you remember the first experiment, right? The first experiment, we were plotting the mass versus the volume of 6 different spheres made of steel, okay? They all had the same density, but they had different masses and different volumes. And the definition of density is given by the mass of the object divided by its volume. If you look for the unit of density, you just do a dimensional analysis, and you find out in the SI system of units, the density has a unit of kilogram per cubic meter. There are a bunch of materials out there in the world. There are a bunch of substances with different densities. And asking you to memorize all of their densities, would be too much, okay? I'm not gonna ask you to memorize the density of 300 substances. No, I'm not gonna ask you that. However, it would be too much to acquire that for you. However, you must remember the density of one very important substance. Not only the substance is very important, but its density is very easy to memorize. The density of water. Can you remember that? The density of water, is easier. It's very easy to memorize it. I'm going to start with the density, not in the density in terms of kilogram per cubic meter, but the density in terms of grams per cubic centimeter. The density of water in terms of grams per cubic centimeter is just this number 1. Water is the standard for density. That's exactly what it means, okay? If you go ahead and do the dimensional analysis, remember that 1 gram is what? Is 1 divided by 1,000 kilograms. And 1 centimeter is what? 1 centimeter is 0.01 meter, right? That's what 1 centimeter is. So by remembering this one here, this easy one, which is just the unit, right? But don't forget the unit in gram per cubic centimeter. You can convert, okay, from gram per cubic centimeter by doing this simple calculation. Okay. And what do you get? Here, 0.01 is 10 to minus 2, right? 1 divided by 1,000 is what? Is 10 to minus 3, right? Let's see what we get. At this point in time, you should know what you get, right? What we get here, when I cube the 10 to minus 2 becomes 10 to minus 6. The meter becomes cubic meter. Okay, and then what do we get? 10 to minus 3 minus 6, right? And when we do this math, you get what? You get 1,000 kilograms per cubic meter. So 1 gram per cubic centimeter corresponds to 1,000 kilograms per cubic meter. That's the density of water. It's not difficult to memorize that, right? So that's the idea that you have to have in mind. Let's take a look at the density of different substances. Here, your book has the density of different substances. You don't have to memorize that. Okay. Solids has a higher density than liquids in general, and liquids has a higher density than gases. In the case of liquids, mercury has liquid mercury has a very high density, 13 times more than the density of water, 13.6 times the density of water. And by the way, the density of mercury, liquid mercury, is higher than the density of many of the solids out there. You see that? The only one is gold, right? Gold has a higher density than liquid mercury. So aluminum is very light. It has this density, 2,700, brass, concrete, and so on. Note that ice has a density lower than the density of liquid water. Okay? Ice is 9,917. Water, liquid water, is 1,000. And that's a nice thing about water. Water has this property, and that's because of this specific property that we are around here. Okay, in general, the solid counterpart of a given substance has a higher density than its liquid counterpart. In general, it's like that. But then there are a few oddballs out there in which the solid counterpart has a density that's lower than its liquid counterpart. Okay? And water is one of those oddballs. And it's because of this specific characteristic property, it's because of this specific property of what that we are around here. that life was able to develop in this planet. If in another universe, water had a different properties in which solid water had a higher density than liquid water, most likely that universe would not be habitable. Okay, and blood is a little bit higher than water. The density of blood is a little bit higher than water. Remember that we are made up of 70% of water, right? It's very close, only 6% difference. Only 6% difference between blood and water. Ethyl alcohol is 806, oil is 800, right? Remember that oil and water doesn't mix. If you're going to mix water with oil is going to float above water. And then we have the density of gases. Density of gases is very low, 1.29 for air, 1.98 for carbon dioxide, and so on, okay? You don't have to memorize this table, but it's good to know, in general, a rule of thumb, the density of gases is lower than the density of liquids, and the density of liquids is lower than the density of solids. Remember, it's a rule of thumb. It doesn't apply all the time, right? Because we have this oddball called water that has a density, liquid water that has a density lower than solid water, which is ice. That's the idea that you have to have in mind. The next concept you must know is pressure. And in order to have a good grasp for both the concepts of density and pressure, you must work out problems, right? Examples that are in the book, okay? So what's the definition of pressure? Pressure is defined, in terms of two parameters that you are already familiar with. And what is this parameter? Those two parameters. Okay, pressure is nothing but pressure is just force per unit area. Okay, or here you go, force per area. Okay, yeah, let's see. I want to take this one out for now. Okay, let me put it aside. Okay, and let me show you an illustration. Let's see, this is not a good illustration that I want. Okay, let me get another one. P37. Oh yeah, here you go. Those are the ones that I want. Okay, here you go. Consider a cube, right? A parallelepiped of mass 10 kilograms. And this parallelepiped has this area of 1 square meter and another area here of half square meter, right? So this parallelepiped that you see right in here is exerting a pressure over the surface. And this pressure is going to be the weight of this mass divided by the area of the contact area of this mass. Okay? In this case, it's going to be the weight is going to be mass times acceleration of gravity, 100 newtons divided by 1 square meter. Going back here. And that's what I was doing here, okay? Consider the cube illustrate the cube, no, the parallelepiped. The parallelepiped. Oh, yeah. Piped. Parallelepiped. Illustrated. It has a mass of 10 kilograms, comma, a larger surface of 1 square meter, comma, and a smaller surface of half square meter. Half square meter. Okay. The pressure that the larger surface exerts, if the let's see, consider the parallel pipe illustrated in the figure. If we place the parallel pipe if we place the larger surface in contact with a horizontal plane, right? Plane. The parallel pipe will exert a pressure given by the following. Okay. Pressure. mg, right? Doesn't change. Kilograms times meter per second square. Area is going to be 1 meter per second square according to the drawing, right? And I'm going to use that later on. Let me paste it here below, right? And let's not forget here it's going to be half meter square. Okay, so 10 times 10 is going to be 100. This doesn't change, right? And what are we going to end up having here? Let's see here. 100 kilogram meters per second square is going to be newtons. And look what we have here. Newton divided by meter square. That's the unit of pressure, which, by the way, we call it, it appears so frequently that we call it a Pascal. 1 Newton per square meter is equal to 1 Pascal. Okay? If instead we put the parallelepiped upright with the smaller surface in contact with the horizontal plane, okay? The new pressure is going to be different. With half of the area in contact with the plane, the pressure is going to increase by twice. You see that happening, right? That goes according to the definition of pressure itself. And by the way, that's a very useful concept of pressure, because we can extend this idea not just to solids, but we can extend this idea to liquids and gases as well, okay? Even though we used just an example for a solid, this idea of pressure can also be extended to liquids and gases. And that's what we call static pressure. That's what they call static pressure. Nothing is moving, okay? Nothing is moving. If that parallel pipe were moving, suppose that you could make it move, right? Try to move, make it try to move. Then that wouldn't be static pressure, it would be run pressure. So that can be extended to liquids and gases, okay? For the case of gases, for instance, let's look at for the case of gases. For the case of gases, you can picture this huge column of air exerting a large weight over your head. Where, remember, we are here in this sea of air, right? The sea of gas, oxygen, nitrogen, carbon dioxide, and smaller amounts of carbon dioxide and other air gases. So you have all those gases on the top of our head, waiting on our head. The atmosphere of the Earth is extend, past 100 kilometers. So you have all this huge mass of air that is waiting on us, okay? If you do the mass, it's possible to come up with a pressure, and it's a good idea that you're going to memorize, okay? It's very easy, it's a very easy number to memorize. We do know that at near the sea level, the pressure due to this sea of gases is said to be 1 atmosphere. Remember that? 1 atmosphere? 1 atmosphere is a very convenient way of remember the pressure of the gases here nearby the sea level. But don't forget, 1 atmosphere, the unit atmosphere is not the SI unit. Atmosphere, the SI unit is going to be your Pascal, your Newton per meter square. When you convert atmosphere to Pascal, it's going to be approximately 101,325 Newton per square meter. Okay? But in general, I tell my students just to memorize, don't memorize this number here. Memorize this number here. It's easier, it's far easier to remember 100,000 Pascal or 100 kilopascal than to memorize this number, right? And if you memorize this number here, you're making just a 1.3% error in your calculations. If you use this number here, you're going to make only 1.3% error in your calculations, okay? That's what I tell my students. Remember that 100,000 Pascal. That's the pressure, that's the air pressure at sea level. If you go to the higher mountains, right, then the pressure is going to be lower because you left below a large amount of gases that are below you that's not waiting on your head. But there is more about pressure. There is more about pressure. There is more about the pressure of gases and liquids, okay? Which, by the way, are also called fluids. Fluids is gas and liquid. Solids are not considered a fluid, but gases and liquids are considered fluid because they can move. Okay, they can flow, right? So pressure is this funny type of force, this funny funny thing, not this funny type of force, this funny thing, right? That exerts a force on you in every possible direction, and not just in the vertical direction, like the weight, okay? So let's see if I have an illustration here for you. Here you go. Here's the same the illustration of my parallel pipe, but now upright, right? It's exerting more pressure here than here. And now, what about this sea, right, of gases that we are submerged on? Here's the Earth, and here's the Earth's atmosphere. I'm exaggerating, okay? The Earth's atmosphere is not that thick at all. It's much thinner than that. The Earth has a radius of 6,500 kilometers, okay? And the Earth's atmosphere is only roughly 100 kilometers thick. 100 kilometers thick is 5% of the 6,500 kilometers here. You can do the math. 100 divided by 6,500. Oh, is it? Wait a minute, it's 1.5%, sorry. Okay? So the thickness of the atmosphere is only 1.5%. So you have to divide this, you know, if you have this much radius here, you gotta divide that how many times? 60 times. And the width, 1/60 of this ratio, is going to be the thickness of the atmosphere. So it's much thinner than what I illustrated here. We made it this thicker so for educational purpose, okay? It's easier for you to visualize something that looks thicker, but remember, this is not in the scale. So if you are at the top, at the bottom of this, at the surface of the Earth, here you go. I am the surface of the Earth right now. At the top, we have this huge column of air that's exerting a pressure on us, on my head, okay? And this column of air has a certain weight, has a certain mass. And when you get the mass of this column of air and divided by the meter square, you get roughly 100,000 newtons per square meter. 100,000 newtons per square meter, okay? 100,000 newtons is like 10,000 kilograms. Weighing on 1 meter square of area. That's the idea that you have to have in mind. This concept applies not just for gases, but also applies for liquids. Okay? Here you go. Here is the concept of pressure of the gases. Here you go, like I said, pressure is this funny type of force. Here's the pressure that the air around this parallelepiped is exerting on the parallelepiped itself. The air around it is exerting a force downward, but it's also exerting forces in the horizontal direction, okay? So this guy, this parallelepiped, not just the parallelepiped, but we ourselves too, we do feel a pressure in this vertical direction and a pressure in the horizontal direction as well. Remember that. Okay, remember that. And now consider a vase. Consider this container. Let's see if did I write that down there? Let's take a look here. Exert a force on you in every possible direction, not just in the vertical direction. But that's for gases and liquids. And consider this container, and we put water in this container. What we're going to do now, we are going to calculate what would be the pressure that a layer of water, a column of water, is going to exert at a different depth. Okay? Here you go. Using this concept of pressure, we can now determine the pressure that a given column of water exerts as you dive deeper and deeper underwater. Okay? That's why I'm illustrating this thing right here. So here you go. In addition to the pressure of the water, there is also the pressure of the air, of the column of air that's above the surface of water, okay? And this pressure, you already know, this 100,000 kilopascal, 100,000 pascal, or 100,000 or 100 K pascal, right? Kilopascal. And this pressure, you already know the value: 1 atmosphere, 100,000 newton per square meter, 100 kilopascal. On the top of that, you're also going to have at this depth the pressure due to the column of air. Okay? And those two pressures are going to sum up. The pressure of the air is going to sum up with the pressure of this column of water, this column of liquid at this specific depth. Okay? It's a very nice calculation. It's possible to do a calculation, very simple calculation that will result in a very simple result as well. Okay? We're going to do that right now. Here you go. Here's the column of water again, right? This column of water has a cross section A that I'm calling. And let's calculate that. I'm gonna calculate just the pressure due to this column of water, and then I will sum this one later on. Okay. So let us. Okay. So let's treat that as an example. Example. Find the pressure due to a column of water at a depth. Find the pressure of a column of water, of height h. Of height h. Okay? That's what this problem is all about. Pressure of this column of water of height h. Right? And the way we do is start with the pressure, with the equation for the pressure. Which is nothing but force divided by area, right? But let's not forget, I told you that the pressure of the column of water is going to be the weight of that column of water divided by the area. Okay? And then we're going to do something interesting here to calculate that in a rather interesting way, okay? I'm going to rewrite my mass. Notice that we have the area here, and I didn't give you the value of the area. But this area that you see, right in here, don't forget this is the mass of water, right? Can cancel out with an area that is implicit in this mass. Can you picture that? I'm going to show you how. You know, remember that density is what? Mass divided by volume, right? Consequently, mass can be written down as rho, the density, times the volume. The volume of that column of water, right in here. And this volume that you see right in here is going to be the height of the cylinder times the area of the cylinder. Can you picture that? And now look what happens. You know, we will be able, here, this volume is going to be A times height. So this A that is here cancels out this other A that is here. Okay. And we end up with something like that. And now look what we got. We got an equation that relates the pressure that a column of water of height h exerts at that depth. And all you have to know is the height of the column, the density of the liquid, or the density of water in this case, and the acceleration of gravity. Okay? If we go back to our values for density of water is what? You know, we have the density of water is what? 1,000 kilograms per square meter, right? No, sorry, per cubic meter. Per cubic meter. Like that. The acceleration of gravity, you know, that's approximately 10 meters per second square. right? And look what the simple equation that we get. We get 10,000. This number 10,000 kilogram per cubic meter. I'm going to put this H right here times H. So the pressure increases linearly with the depths. And I can also start to cancel, right? This meter cancel out is this meter cube. Okay, the second square get like that. Let's not forget that we still have a unit of meter right there in H. Okay, if we multiply, let's go back to what we had before, right? Let's multiply the meter here upstairs with the meter downstairs, right? So what we get here, we had kilogram meter per second square, right? We still end up with the unit of pressure. Kilogram meter per second square is newtons. Oops, it's newtons. And we get this cubic meter. Why do we get this cubic meter? Because this cubic meter cancels out with the meter implicit here in H. And we end up with a unit of Newton per meter squared. Okay? Which, by the way, right? I can here write it down. 1, 2, 3, 4. I'm going to put in powers of 10 so you can save some space. Okay. No, note C that for every 10 meters of depth, we get a pressure variation of, it's something interesting about water, you know? Water is, find the pressure column of water. If you dive 10 meters deep, what you're gonna get? You're gonna get an added pressure of 100,000 pascals. See that? Which is, by the way, approximately 1 atmosphere. So for every 10 meters that you dive underwater, the pressure increased by 1 atmosphere. So 10 meters underwater. So if you dive 10 meters underwater, you will feel a pressure of 2 atmospheres. Okay, 1 atmosphere due to the outside air, and another atmosphere due to the water pressure. Another 10 meters dive, another 10 meters underwater, or 20 meters corresponds to a net pressure of 3 atmosphere approximately, right? And so on. Can you memorize that? That's not difficult, right? So I'm gonna even put a table here. Insert table like that. I don't want the table to go to, you know, depth. Okay, H stands for depth. And I want lowercase h, 0, 10, 20, 30, 40, 50, 60, 70. And what would be the pressure I'm putting ATM, right? Here's going to be 1 atmosphere, 2 atmosphere, 3 atmosphere, 4 atmosphere, and so on, right? 6 atmospheres, 7, 8. I will boldface this one. Okay, but let's not forget the above equation corresponds to a pressure due to a static fluid. In other words, a fluid that is at rest, not moving, okay? If the fluid starts to move, then the problem becomes a little bit more complicated. Then the problem will become a little bit more complicated to derive. It's not that difficult, but unfortunately, we don't have time to cover that. But I want you to understand the difference, okay? And I'm going to give you a very simple example. Think about, you blowing air in your hand, right? Like that. When you blow air in your hand, you feel some pressure due to the air colliding against you, right? You feel some force, right? And this force, what is that? Is an additional pressure that the motion fluid is exerting on your hands. This type of pressure is called ram pressure, RAM, okay? If you have, for instance, a fluid like air blowing towards your hand, you will feel an additional force that is producing an additional pressure. This is not a static pressure. This is dynamic or ram pressure. Okay? We're not going to cover ram pressure here, but it's important that you understand the difference. Okay, understand the difference between static and ram pressure. What time is that? 11:06. Let's see, there is one more. So we cover 11.1, 11.2, 11.3. And I want to cover 11.6 now. Okay, we're skipping, right? 0.4 and 0.5. Let us cover 11.6 now. Archimedes principle. By the way, today I was watching a very nice video in YouTube telling us about Archimedes. That guy was a genius, okay? The guy was a genius. He used to live there in ancient Greece. And this, I think he should be considered the brightest scientist ever lived. Okay, let me see if I can find the video there on YouTube, which I recommend you to watch. Okay, Archimedes starts thinking about ideas that became commonplace only 1600 years after himself. Okay, 1600 years. Let's see if I can find it here. Archimedes. Archimedes. I will have to type here Archimedes. Not Archimedes' principle, but the life of Archimedes himself. I will watch it today. The greatest mind in ancient history. I will go further than that. I don't think he was the greatest mind in ancient history. I think he's the greatest mind of all time. Okay, it must be this one. Yeah, it's this one here. I like this video. Here they explain how Archimedes managed to calculate the area of a circle, which, by the way, was the very beginning of calculus, integral and differential calculus. Archimedes started to struggle with this concept of integral and differential calculus. Okay, and that's the one. Let me put this here.
Mathematicians of all time. In addition to writing a number of.
Okay, so he wrote a number of books at a time that we didn't have printed press. Remember, printed press was invented only in the 1500s. This guy lived, 100 years before Common Era. And I'm going to put this link. Check this video in YouTube about the life about Archimedes' contributions to science, contributions to math and science. This guy was murdered by a Roman soldier when the Romans were invading that place where Archimedes was. And today I wonder what would be of the world if Archimedes had not been killed by that Roman soldier, right? The Roman soldier was under explicit order of not killing him because the bosses there, they want to have Archimedes on their side, working for them, okay? But unfortunately, he was killed by the soldier, right? I do not know what happened to the soldier. Here you go. Check this video YouTube about Archimedes' contribution to math and science. This one right here. And of course, there are many more other videos about Archimedes. The other ones must be good as well, but I didn't watch them. Okay, see how many videos we have about Archimedes principle, which we're going to cover right now. Okay. I'll take him, but let's Archimedes principle. See, this is a device that Archimedes invented. We call it Archimedes turbine. It's a way of moving water uphill. He invented that at his time, and we still use something like that today. It's a screw that pumps water uphill. Screw turbine. All right, but let's talk about Archimedes principle. What you have to know Archimedes principle is a very simple idea. Going back to our container with water. Consider this container with water with an object submerged under the water. Here's my object, actual object. Okay, you already know there is some pressure here due to the air, right? But there is also some pressure of the water plus the air at the top of this object, right? Because all this top line here of this object is at the same depth, the pressure here is the same as the pressure here is the same as the pressure here, right? The pressure, depends only on the depth. Well, likewise, we are going to have that the pressure here on this side is going to increase as you go deeper and deeper. And the increase is linear with the depth. Picture that? It applies not just to this left side, but applies also to the right side of the object. Okay, apply not just to the left side, but applies also to the right side. And then, remember that I told you, pressure due to fluid is this funny force that exerts a force in every possible direction. Can be downwards, can be sideways, can be upwards as well. So here you go. At the bottom of the object, we have a higher pressure than at the top because it is a higher depth. This force here due to the pressure cancel out with this force. This other force here cancel out with this force. In the horizontal direction, the net force is going to be 0, right? But in the vertical direction, the net force is not going to be 0. The net force is going to be upwards. And this object that's underwater will feel lighter because of this net force. This net force has a name. It's called buoyancy force. Buoyant force. Okay? That's why we feel lighter underwater. We feel lighter underwater because the pressure from the bottom of the body is higher than the pressure of the top of the body. At the top of the body. Okay? So you go. Did you get the idea? So Archimedes, he figured that out. He figured out that we feel lighter because of this variation in the pressure as we go down, further down. Okay? And then there is more. Let me write it down, right? So I document that for you. Remember that pressure increases with depth, right? Consequently, pressure is going to be higher at the lower extremities, right? The lower regions of an object if compared with the higher regions for the human body. So for the human body, if you are upright underwater, the water pressure at your feet will be higher and upwards, right? Upwards than the pressure at your head, which is going to be downwards. Then the downward pressure at your head. This differential in pressure results in a net upper pressure. The net upward pressure. Pressure that produces what we call a buoyant force. Buoyant force. That is why we feel lighter underwater. Right? Next, what's next? Okay, that's just qualitative, right? What we're doing here is just qualitative. Now let's apply those qualitative ideas to find some more, something that's more quantitative. How can we quantify? The next question is, how can we quantify this qualitative idea, right? That is buoyant force, that is buoyant force. Okay, there's a way to do that. At this time, Archimedes discovered the following. He was reasoning, right? He was trying to make sense of this phenomenon of buoyant force. He was trying to quantify this phenomenon of buoyant force. So he started to do actual experiments, okay? Even the experiment that he did in his own bathtub as well. We all know that when we submerge, when we go into the water in the bathtub, the level of the water rises, right? We all know that. Here you go. We have this object right in here in this container. If we submerge this object just like we did here, what happens to the level of the water? The level of the water rises, right? See that? Archimedes saw that, he started thinking about it, and then he came with an interesting conclusion. He didn't do any mathematical calculation, okay? He just assumed that, that the weight, what did he assume? He assumed that the weight of this displaced mass of fluid or this displaced mass of water was equal to the buoyant force. Okay? At that time, he didn't have how to prove that mathematically, but he figured that out by himself. And then at that time, it was called the Archimedes principle. Okay? Very important. And nowadays, we can calculate that. It's possible to calculate that using that formula for the pressure of the water as it goes deeper and deeper. Let me see here. Watch it, space dock channel, Professor. No, space dock channel. No, what's it all about, Ridwan? Is that a YouTube channel? Space dock is a YouTube channel? Sorry, I just saw your message right now, Ridwan. Are you there? Yes. What is that? A YouTube channel, Space Dock, or it's a TV channel? It was in your YouTube. That's why I asked. I see. Space Dock. Let's see. It was in your YouTube feed. You mean writing here in my? Let's see here. Space Dock. Space Dock. Okay. Okay, I see some starships here. Okay, spaceships, and I saw the Spence there too, right? The Spence is a very good. Okay. No, I haven't seen, but now that you mention, I'm gonna look at it some other time. Okay, and they also mentioned the expense, right? Okay. Expense. See, they have also expense here, but that's unrelated to Archimedes principle, right? I thought yeah, okay. Yeah, I'll take a look at that. But let's go back here, right? So here you go. Archimedes principle. Discover the following. One, when you submerge an object completely underwater, right? This object displaces its own volume of water. Simple enough? That's simple enough, right? This is not Archimedes principle yet. It's just kind of obvious, right? Why is that? Why is that? That is because two objects cannot be collocated at the same time, right? Right? So here you go. I'm going to illustrate that right in here. See here? This water displaces upwards because this water here cannot be collocated with this object. Okay? So if this object has a volume V, he must displace the same volume of water. He must displace the same volume of water, because they cannot be simultaneously collocated in the same space, in the same space, in the same volume, right? This is not Archimedes' principle yet. Okay? Collocated simultaneously, right? Simultaneously. Simultaneously. Okay. What Archimedes reasoned at his time was the following. You know, concluded, reasoned, let's say, not reasoned, but concluded at his time is what his time is what we call today Archimedes' principle. And then what's Archimedes' principle? The buoyant force is equal to the weight of the volume of the displaced fluid. Okay. So I'm going to give you an example. Example of Archimedes' principle. Okay, a 1 cubic meter, an object, a solid object with a 1 cubic meter volume, 1 cubic meter volume is completely submerged under water. Okay? Determine the value of the buoyant force applied to this object. Okay? And then using Archimedes' principle, determine the value of the buoyant force applied to this object. Solution. Okay? Archimedes' principle states that the buoyant force is equal to the weight of the displaced fluid. Displaced fluid, well, which is the fluid? Water, right? Displaced water, which is the fluid. Okay. The volume of water that is displaced is what? I already mentioned right to you, right? Is 1 cubic meter, 1 cubic meter, right? One like that. So all we have to do is to determine the weight of this volume of displaced water, right? And we do like the following. Remember, here we go. Don't forget that mass of the water is what? Density times volume, right? The density of the water is 10 to the cube kilograms per cubic meter. The volume of the water is 1 cubic meter. The volume of the displaced water is 1 cubic meter. I'm going to put it at here, displaced volume of the displaced water. Here's the volume of the water, the volume of the density of water. right? So 1 cubic meter of water is exactly 1,000 kilograms of water. The buoyant force is going to be what? Is this mass multiplied by G, right? The buoyant force is this mass of the displaced fluid multiplied by G, which ends up being 10 to the 4 kilogram meter per second square. Okay, and 10,000 is 10,000 newtons, or 10,000 newtons. Okay. Makes sense. So there are 3 steps, right? The first step is to determine how much fluid, what's the volume of the fluid that's displaced. That's the first step. The second step is to calculate the weight of that fluid that was displaced. It's 11:30 right now. Let's take our little break. I hope I can finish this chapter today. Yeah, we'll be able to finish this chapter today. And we're going to be finishing, when we come back, we're going to continue using this idea of Archimedes' principle to find something interesting about, what boils up and what sinks, right? When we come back, let's write it down. When we come back, I will show you how to use Archimedes' principle to determine what object will float and which object will sink under a fluid. Okay. Okay, so break from 11:30 a.m. to 11:45 a.m. I see you in 15 minutes. Okay, so I'm back here, and let's use those last 15 minutes to finish this chapter, okay? And then next time we start something new. What we're going to do now is to find out what are the conditions for an object, What we're going to do now is find out what are the conditions for an object float, sink, and remain at the same depth. This condition is called neutral buoyancy. Neutral buoyancy. Okay. And if you ever practice scuba diving, they teach you how to remain neutrally buoyant underwater, which is a very useful skill to have in case they want to stay at the same depths all the time. Okay. Fishes, fishes are master in being neutrally buoyant. Okay. So underwater conditions, an object will sink, float, or become neutrally buoyant. Okay. So let's start with sinking, a sinking object. A sinking object. An object will sink. Here you go. An object will sink whenever the net force applied to it is downwards. Do you agree with me? It's downward, okay? So if you have, going back here to my drawing, right? So here you go. You have this condition here, the weight of the object is larger than the buoyant force, then the object will definitely sink. Make sense? There's no other force here, right? Just the buoyant force and the weight of the object. Don't forget, we are doing that. We're assuming that there are only static forces that are being applied to this object, right? So a sinking object will have the following, we will obey the mg, the following equation: minus buoyant force must be greater than 0, right? And then it will sink. Let's see if we can do better than that. Just that just doesn't tell us much, okay? And by the way, an object, let's see, I'm gonna put it, as a completely submerged object. It's gonna be like that, completely submerged object with volume V, okay, will sink whenever the net force applied to it is downward, okay? Assume that we're talking about water here. Submerged object in water having a volume V. Here's the mass of the object. Here's the acceleration of gravity. Let's not forget that the buoyant force is going to be given by the weight of the displaced water, right? That's what we have. But we can do better than that. We can do better. What can we do? We can write down the mass of the object in terms of its density, its volume, and the acceleration of gravity. And we can do the same for the water as well. Density of the water, I will make clear that is exactly water, nothing else. The volume of the displaced fluid, which is coincide with the volume of the object because the object is fully submerged, right? Must be greater than 0. And now I'm going to do another step. Here's the density of water. The volume of the displaced fluid is going to be equal to the volume of the object, and this thing here is going to be greater than 0. And now that I have this equation, look what's going to happen. We're going to discover that here go, V and G are going to cancel out, right? So whenever the density of the object minus the density of the water is greater than 0, the object is going to sink. Even better. I'm going to write it in a different way. Whenever the density of the object is greater, the density of the object is greater than the density of water, the object will sink. Isn't that nice? So if you have a density higher than the density of water, you will sink. Okay, that's why styrofoams float. Okay, they don't have a density greater than water. They have a density less than water, and we can do the same for the rest. 8 more minutes to go. A completely submerged object in water have a volume will float whenever the net force I'm gonna do it here. Find the relation between the density of a object and the density of the water whenever, well, whenever you know what? Leave it this way. I'll take it out. Leave the way it was before. Now we're going to repeat for, right? Object float, okay? An object will float whenever the weight, okay, I will repeat exactly like I did before, right? Whenever the weight minus the buoyant force is less than 0, right? Here you go. Let's see here. Let's see if I have an illustration here. Okay, here you go. That's the illustration. In this case, the object will float because the buoyant force is greater than the weight of the object. Okay? And just like before, you know, I can write down the buoyant force as the weight of the displaced water. The mass of the object is the density of the object times its volume. And same thing applies for the water. The volume of the displaced water is equal to the volume of the object. And let's not forget, we have less than 0 here. And just like before, not just like before, the sign here must be exchanged, right? So here you go, what we find? We find that the density of the object must be less than the density of water for it to float. Okay, and then we can do the last one. At this point in time, you should know what's gonna be the final result, right? For will float, but will remain neutrally buoyant, whenever the net force applied to it is 0. Okay, that's what fishes are master at doing. Okay, let's see if I have neutrally buoyant. Yeah, I don't have here neutrally buoyant, but neutrally buoyant is the weight equal to the buoyancy force. Okay, so whenever mg minus b is equal to 0, the object will be neutrally buoyant. And then we go ahead, repeat exactly what we did before. Okay. The procedure is exactly the same as you did before. Write down the masses in terms of the density and the volume. Okay, it's very convenient to write that down in terms of the volume because the volume of the displaced water is equal to the volume of the object itself, right? The object is completely submerged, and just by recognizing it, we end up canceling out the volume and the acceleration of gravity. And so what we conclude? We conclude that the object will be neutrally buoyant whenever the density of the object is equal to the density of water. Okay? And that's something that you can practice in the swimming pool. Okay? You can practice the above in the swimming pool. Why is that? They are both in a swimming pool, but make sure that you're not going to drown, right? Swimming pool. How, right? How? Well, simple. Simple, okay? The density of the human body is very close to the density of water. Remember, 70% of the human body is made of water, right? And on the top of the water, we also have some organs that are full of air, like the lungs, okay? But it's not that it's just very close to the density of water. There's more to it. But wait, there's more to it. right? But wait, there's more to it. It's not only very close to the density of the water, but the density of the human body can be adjusted just below and just above the density of water within a range, right? It can be adjusted within a range just below and just above the density of water. How do you do that? How do you do that? How do you do that? Just by breathing in and breathing out. Can you picture that? When we breathe in, right? We suck air into our lungs and our overall density becomes less than the density of water. At this point, we float. However, when we breathe out, right, our density becomes our overall density, right? Our overall density becomes greater than the density of water, and we think, okay? That's how we can. Okay, so if you go to the swimming pool, well, we have one more minute to go, right? If we go to the swimming pool, preferably with a snorkel, okay? Preferably with a snorkel. You know, hold, exhale, and keep like that, stay like that. You will notice that you will sink little by little. I already done this experiment in the water when I was swimming. So, likewise, when you breathe in, you will revert your motion back upwards. Your motion back upwards and will float, okay? And that's what we have for today. It's already 12:01. Okay, I'll be here another hour. If you don't have any questions, we can stop now. And if you do have questions, like I said, I'll be here.
I have a question. I have some questions.
Yeah, go ahead.
It's about homework
Yeah.
question. Homework 8, chapter 7, linear momentum.
Okay. Let's see here. Linear momentum. Not this one, right? I want this one. This one. Homework 8, linear momentum. Yes.
Question 4.
Question 4. Okay.
Oh, yeah, that one. I don't get I couldn't really get the right answers for B, C, D, E.
Okay. Initial speed at a height. Okay. At 278, ball swings downward and striker is at rest. This ball is at rest. Use the principle of conservation mechanical energy. Find the speed of the 278 kilogram ball just before impact. Let's see, just before the impact. Use the principle of conservation mechanical. That's easy, right? You have the height here.
Mm-hmm.
Right? You get the potential energy and the kinetic energy. The potential energy plus the kinetic energy here must be equal to the potential energy plus the kinetic energy just before the ball strikes. Okay? Did you do that?
So no, I don't know how to do it. So potential energy is the mgh, right?
Yeah, mgh.
And kinetic energy is 1/2 times mass times velocity
half mg square. Half mg
Yeah.
square.
mg square. Oh, it's mg square. Okay.
Yeah, half mg square.
Yeah, so
Okay.
can you show me how to do it? Like on my
Okay, using the principle.
I only have one attempt and I don't want to like lose bunch
Burn
of
it.
points.
Okay. Let's see right here. Insert page break. Right? Question 4, you said?
Yes, question 4. Chapter
Homework
7.
8. Is that right?
Yes.
Okay.
Oh,
So
homework 7. Oh yeah, homework 8, chapter 7, linear
7.
momentum.
Okay, so here we go. So it's like that. Half m1 v naught 1 is square, right?
Mhm. That's the kinetic energy, right?
Yeah, kinetic energy, initial kinetic energy plus initial potential energy is what? M1 GH, right?
Yeah. That's the kinetic. Oh no, that's potential energy.
Okay.
But here's the thing that I don't get. Like uh, I I got the formula, but I don't know if I have to like subtract each other's and stuff like.
One minute. Let's see. What's the problem? I didn't understand. You.
So the B.
Oh man, we are doing A, right?
Oh no, I got the right answer. I got the right
A
answer.
you got. A you got.
Yeah, A I
Okay.
got it, but
Okay.
from B to E I got everything wrong.
Okay.
Like
Let's do the other ones. Okay.
yeah.
Assuming that the collision is elastic, find the velocity, magnitude, and direction of the 278 kilogram ball just after the collision. Okay. Okay, so here you go. You found the V find. Okay, from item A, you found V final of 1, right?
Mhm.
Right?
Yes.
That's what you. Okay, now that you found V final of 1, okay, we're going to do is elastic collision, item B. Okay,
Mhm.
so you gotta do conservation of momentum, right? It's one dimensional. V final 1 plus M2 V final 2, right? Equal to M1. So let's see, instead of V final 1, let's call it a different way, okay? You found, instead of V final 1, let's call it velocity at the lower, right? The lower region, L1, right? Okay. So here you go. MV final 1 plus M2 V final 2 is going to be equal to M1 V initial 1, right? Conservation of momentum, right? Okay, but let's not forget that the initial velocity of 1 is going to be that one that you calculated before, that I call VL1, right? Okay. So what did you want again? Let's go back here. Assuming magnitude and direction is asking find the velocity, magnitude and direction of the 278 kilogram ball. Okay. So he wants this velocity here. Okay. That's what he wants.
Okay.
Okay, so now it's gonna be like that, right? Next, we pass this one to the other side. We do not have F2, right? We still do not have F2, right?
Mhm.
Right? So let's
Yeah.
highlight it. How do we find VF2?
You have to move to the left side and move the mass one mass I mean velocity, final velocity one to the right, right?
Well, I didn't quite understand what you mean, but well, it's elastic, right? Elastic collision. In elastic
Ele-
collision, the
Oh
momentum
yeah,
is
elastic
conserved.
collision.
What else is conserved?
I don't know.
Well, elastic collision, you have conservation of momentum and you also have conservation of energy.
Conservation energy.
Okay.
Okay.
Okay. So you're gonna need another equation here. Okay. So here you go. I didn't put. I should have put it here. Let me put it here.
Mm-hmm.
Okay. Half
Uh-huh.
M1 V final 1 square minus half M2 V final 2 square. What else? That's after the collision. After one collided with two. And then before one collided with two. Two was at rest, right? So I don't need to do conservation of energy at that spot, right?
Yeah.
Now you have two equations at two unknowns. You go. In principle, you should be able to solve this system of equations, right? You already have this one here that you calculated before. Can you do that?
Yes, but can you show me how to do it, like actual number? Because like I know this is kind of weird to say, but like I only have one attempt. So if I make like
I know, but did you try that when you were first trying to solve your problem?
no, I had like different equation. So mine was like way simpler than this. So what I did was like I did the mass sub one velocity final, the final velocity one, like I did like fraction. I applied like weird formulas to find the value. So I just realized that I did it wrong.
Okay. So you must have, conservation of momentum, right? Equation of conservation of momentum and conservation of energy. That you didn't use conservation of energy, right? That's what you're telling me.
No.
Okay. So item B. Okay. So here you go. Let me erase that. Let me stop the recording. Stop recording. Where's the recording here?